And now we're going to move to the invited lecture by Professor Daniel Mandler from the Hebrew University. So Danny is really a persona in Israel for the chemistry and for the electrochemistry. He's well known for mainly his precise work in analytical chemistry, sensing, and also power sources. For me, he's a mentor, so we have every 2 weeks, we did not do for a long time, but we have a discussion, and he's really open to mentor young folks. He's going to talk today about nano to nano, so Dawn really gave a fantastic background for the talk of Danny. So thank you, Danny.
Okay. Thank you, David, and thanks for the organizer. It's actually a pleasure to be here, and I hope that we will renew this tradition of having the Israel Electrochemistry meeting every year in another university. So thanks for the organizer and Diana for doing all these things. So within the next 25 minutes, and since you're freezing, so this will make you be awake, I'll try to show you what we have been doing for quite some time. And well, let's jump. So I guess everybody is very much familiar with electrochemical deposition, what is sometimes called electroplating. Most of you actually think that everything started with Faraday, but actually there were previous people who did the work even before Faraday, especially Ventelli from Italy. And the question with that is, what can we renew after 150 years of electrochemical deposition? And what I want to show you actually two different concepts that we have been using for some time, and there is plenty of place for other players here. And the idea that I want to show you is, one is what we call indirect deposition, and the other one is nano-deposition, and everything will be combined together, and I'll give you some examples. And what is it good for? So nowadays, when we talk about electrochemical deposition, obviously we want to make something much more sophisticated than what Faraday was trying to do 150 years ago. And again, I'll show you some examples. Okay. So when you think about the very simple experiment that Faraday was doing, okay, taking either silver ions or copper ion in solution and reducing them and causing the product, which is much less soluble in water than the ions, to deposit on the electrode surface, obviously this was limited to compounds or to ions that are electroactive. But what happens if you want to make, or if you want to deposit things that are not electrochemically active? How can you do that? An example is, if you want to deposit a metal oxide such as zinc hydroxide. In this case, you cannot reduce the zinc like Doron just said before, because you're going to reduce the protons before. But instead of reducing the species that you want to deposit, you change their environment. Which means, for example, by reducing water and changing the pH, elevating the pH on the electrode surface, in the presence of zinc ions, you will cause the deposition of zinc hydroxide. You can do that in many different ways, and I'm going to show you how we actually using that. The advantage of that is, first of all, that you can obviously deposit a variety of things that you cannot deposit otherwise because they are not electroactive. You're not limited to electron transfer, which takes place only a few angstrom from the electrode surface. You can do much farther because you can actually draw things into the diffusion layer and so on. So this is one concept. The other concept, again going back to Faraday, think about what he did. He always started with ionic or atomic molecular species. But this doesn't really make sense. If you want to make something more sophisticated, it's much better to start working with bigger building blocks. Why not to start working with nanomaterials? So the idea is, and this is shown schematically or in a cartoon here, if you want to make a building, obviously you don't start with sand. You start with bricks. The same thing is with electrochemistry. Why to start making a film, whatever you want to make, out of ions or atoms or molecules? Why not to start with a little bit bigger building bricks, which means nanomaterials? How can we combine everything together? So let me start with the indirect deposition. And a very good case is the electrochemical deposition of sol-gel materials. If you think about sol-gel, and for those of you who are not familiar with sol-gel materials, so sol-gel materials, you can call it how to make glass at room temperature. Obviously, everybody is familiar with the industry of glass, and glass is a high thermal procedure because you start with a polymer, you start with silica. But with sol-gel, which is not limited to silicon, you start with the monomers. Monomers that have this type of structure. And again, it doesn't have to be silicon, it can be also zirconium, aluminum, and so on. And you hydrolyze the monomers, okay? And then the monomers, actually the hydrolyzed monomers, they undergo condensation, which is polymerization, to form the silica. The big advantage of sol-gel that I guess most of you are familiar with is that you don't have to start with materials that have 4 different monomers that will go, 4 different ligands that will hydrolyze. You can replace one or more of them with other groups. For example, if you have here a silicon-carbon bond, this will not hydrolyze. And because of that, eventually your silica will always have on one silicon atom, you will have a group that will give different properties to the silica. You can make, for example, hydrophobic silica, you can make charged silica, and so on. That's a big advantage, besides the fact that you don't do that at high temperature. So, in fact, if you look at the process of sol-gel, sol-gel is not an electrochemical process. It's basically an acid-base reaction, hydrolysis and condensation. And in fact, and indeed, all the ways until recently, the way to make sol-gel material is by deep coating, spin coating, spraying, and so on. How can you do that electrochemically? You can do that by understanding that both of these processes, the hydrolysis as well as the condensation, are very sensitive to change of pH. And you can see here that the rate of hydrolysis and condensation actually accelerate both at acidic as well as basic conditions, which means that if we change the pH on the electrode surface, we can accelerate and we can basically catalyze the sol-gel formation. And indeed, that's exactly what you can do. Here, if you use protic solvents such as water or alcohol, and if you, for example, reduce the solvent, you elevate the pH, you form a gradient of pH from the electrode surface to the solution, and vice versa. If you oxidize water or alcohol, you decrease the pH. And because of that, you catalyze and you cause the deposition of the sol-gel. And in fact, this works very, very well. A big advantage of that is shown here. What you can see here is we took a chip made by Intel. You can see that the bright spots are made of aluminum. The black spots are actually an insulator made of silica. And this is a comparison of depositing titanium, in this case, not silica. This is the regular deep coating, and you can see that the titanium coats the entire chip. Whereas if you use electrochemistry, because you change the pH only on the surfaces that are conductive, because of that, the sol-gel, in this case the titanium, deposits only on the conducting parts. And by that, you can also, as I'm going to show you, can also do, and you can coat and deposit the sol-gel on very complex geometries. That's a big advantage as compared to the other methods. So this was actually the first paper we published. Nowadays, there are tens of laboratories all around the world that are using the same methodology. By the way, you can control the potential, as you can see here, and as you apply more negative potential, obviously the gradient of pH is higher, and because of that, the rate of deposition is also higher. I'll give you only 1 or 2 examples from here. We have been working a lot on coating of medical implants, and what you can see here is a stent. That's a very, very big industry, multi-billion industry. And the problem with stents that are made of metallic parts, normally nowadays they are made of cobalt chromium alloy, that first of all not always biocompatible, and because of that, the body tries to reject them. You get a phenomena which is called restenosis, and because of that, in many cases, you have to replace the stent after a few months. Because of that, actually, there is an industry which is called drug-eluting stents, in which these stents are coated with a polymer that makes it more biocompatible, and at the same time, it's a matrix to release the drug exactly where you want. What did we do here, or how did we use the fact that we can deposit soldier? So we synthesize this dimer, as you can see it here. So this part of the silica, you can see here is a silicon carbon bond, and here you can recognize polyethylene glycol. Polyethylene glycol is a polymer which is very hydrophilic, and because of that, it prevents the formation or the absorption of proteins, bacteria, and so on. So we coated the stent electrochemically. Here is the cell of the stent. You can hardly see that it's actually coated. And here you can see we have very good evidence that indeed the coating is there. And then once you expose it to red cells, you can see this is an uncoated surface, this is a coated stent, and you can see that on the non-coated stent, actually the red cells proliferate and they grow and so on. On the coated surface, almost nothing grows. So this is one example. What else you can do with that, with this indirect deposition? You can also add to the soldier different materials, such as carbon nanotubes, graphene, nanoparticles, and so on, providing that they interact somehow with the monomer. And because of that, you get co-deposition. So the soldier, once it deposits, it takes with it the different materials you add to the solution. And again, I'll give you only one example, and this is with carbon nanotubes. You make a dispersion of carbon nanotubes. Inside the solution, you add a soldier monomer. This is the tetramethoxysilan and so on. You apply a potential, and you get very nice deposition, as you can see here. Here, you get actually a deposition which contains the carbon nanotubes, the rate of deposition, and also the ratio between the soldier and the carbon nanotubes depends very much on the potential. You can see that the deposition does not take a long time, and then you can actually analyze it and so on. Again, one application we did with Rafael, what you see here is actually a wafer made of a semiconductor which is sensitive to the IR. This is a silver net which was printed, and they wanted actually to coat this silver net with a black material so it will not reflect the light. So as you can see here, we took the entire wafer, we dipped it in the solution, we apply potential, and what you can see here is because it deposits only on the conducting parts, the carbon nanotubes and the solder, which actually enforces and actually makes it much more rigid, deposits only on the conducting parts. Let's switch to the other part. The other part is actually electrochemical deposition of nanomaterials. So I said before, why not to start with nanomaterials? Which means that nanomaterials, obviously, as you know, they don't dissolve in the solution. You have to disperse them in the solution. And once they are dispersed, what we want to do, we want to apply potential and to cause their deposition. If you learned a little bit about when I was young, it was called colloidal chemistry. Now it's called nano, because everything is nano. So the idea is, how can you do that? So if you know the nanomaterials, when they are dispersed in solution, they tend to spontaneously aggregate. And the reason for that is that as you make the material, if you make the materials smaller, because of also the curvature and so on, their surface energy actually increases, which means that if you have nanomaterials in solution, they will spontaneously aggregate. And this requires actually to stabilize them and to introduce some kind of a repulsion between the nanoparticles in order to prevent this spontaneous aggregation. And there are two ways to do that. One way is an electrostatic repulsion, which stabilizes them because they have the same charge, which means that they repel each other. The other one is steric repulsion. Everybody who works with gold nanoparticles in organic solutions know that you can stabilize them simply by absorbing a tile, a long chain tile, which physically prevents their spontaneous aggregation. So now the question is, or the challenge is, how can you diminish, how can you lower this repulsion by applying potential? And one way to do that is, again, by changing the pH, which will change the charge of these nanoparticles. Again, one or two examples. Going back to these metal implants, this morning we heard Noam Elias from Tel Aviv University, and that's something we have been doing with him. So we are very much interested to coat orthopedic implants. As you might know, that orthopedic implants are mostly made of titanium because of the strength. Titanium is biocompatible, but it doesn't have this very special property which we call osseointegration. Osseointegration means that it actually promotes the formation of a bone. You know that if you implant such an implant, you want actually that it will hold the bone together, and after some time you can basically remove it because the bone starts growing. The problem with this titanium that it does not have this property. It doesn't cause the bone to grow, and because of that, nowadays what normally is done is that they take these titanium implants and they coat them with the main component of the bone, which is hydroxyapatite. And this is a very, very sophisticated process. It's done at very high temperature, above 1,000 degrees, by electrospraying, and obviously you cannot introduce by that any organic material. So again, how can we do that? We synthesize nanoparticles of hydroxyapatite, which is very, very low, have very low solubility, and we stabilize in order to prevent their spontaneous aggregation. We stabilize them with different carboxylic acids, such as polyacrylic acid or even citric acid. And then, in this case, we apply positive potential, which generates protons on the electron surface, and because of that, we partially neutralize the negative charge of the carboxylic acid, and we drive their spontaneous deposition. And indeed, it works very well. I have everything here. I'm not going to go into details, so we synthesize, we have very good characterization of the hydroxyapatite nanoparticles, and then you can see here very nicely, first of all, in solution, you can see what happens to these nanoparticles that are stabilized with carboxylic acid. As you go to lower pH, they simply precipitate. Okay? And here you can see how the zeta potential changes as a function of pH. Obviously, as you go at a pH lower than the pK of the carboxylic acid, the zeta potential becomes close to zero. And you can see also here that the size of the nanoparticles obviously increase. So here you can see this is the deposition, okay? And the beauty of this approach, and that's why we call it from nano to nano, because we start nano in dispersion and we end nano, still nano on the surface. The deposit is still made of the same nanoparticles. And again here, with the potential, you can control the rate of deposition. The next step, here we can see also that indeed now such a screw, which is actually used, made of titanium, which was coated with this hydroxyapatite, it indeed has this osseointegration property. It promotes the formation of bone. But what is more interesting is to go to the next step. And to the next step means that now, because everything is done at room temperature, you can obviously add to the nanoparticles any drug you want. And in this case, we added two different antibiotics, as can be seen here, in a very simple way. You synthesize now the nanoparticles, you add your antibiotics, and you actually load the antibiotics with nanoparticles. Here there is the analysis by three different independent methods, how much antibiotics we have in this hydroxyapatite. You can see it varies between 10 to 12%. And again, we have everything here is shown, the deposition, and we characterize the deposition and so on, but I will skip that. We'll show just only this case that indeed the hydroxyapatite nanoparticles after deposition have still an antibiotic, very clear antibiotic activity as compared to the hydroxyapatite, which are not loaded with antibiotics. So this is one way. One way to cause their destabilization is by changing the pH. But you can do it also by another way. And another way is to change the ionic strength. And this is, if you know, and this is an experiment to do at home, not like what Doron showed before. With mercury, you better not work at home. So, and better not hold such a vial with your hands. But here, what you can do is, if you take milk, which is basically a nano-dispersion of small oily drops that are stabilized with casein, with the negatively charged protein, if you add to the milk, if you add a spoon of salt, you will immediately see that oil separates from the water. And the reason for that is that you increase the ionic strength. Increasing the ionic strength obviously causes the diminishing of this repulsion, of the electrostatic repulsion. So how can we, by electrochemistry, how can we increase the ionic strength? And to do that, in a very simple way, and not to change the pH, okay, we simply took a copper surface and we pulsed it with a short pulse of potential, a positive potential, which generated a flux of copper ions. We generated a flux of copper ions on the electrode surface, increasing the ionic strength and causing the deposition of the nanomaterials. Just to show you how this works, for example, if you look, this is VO2 nanoparticles. VO2 nanoparticles are thermochromic materials. You can see how the average size of the nanoparticle changes as we increase the concentration of different salts. Obviously, if you use doubly charged salts such as copper chloride, you need much lower concentration in order to cause the precipitation. So again, how can we do it electrochemically? Instead of using a continuous copper surface to show that it's indeed because of electrochemistry, we use a copper grid. Okay, here you can see an optical micrograph of the copper grid, and you can see the 4 different nanomaterials. So these are the VO2 nanoparticles, gold nanoparticles, carbon nanotubes, and graphene. And you can see very nicely how only the copper grid is coated with the nanomaterials. The nanomaterials do not change their shape. They are still maintained their nanoparticular structure. And the third way of doing electrochemical deposition of nanomaterials is simply doing a redox reaction. And this is shown here with another quite well-known material, which is tungsten oxide. Tungsten oxide is the most common electrochromic material, okay? And nowadays, even the windows of airplanes are coated with tungsten oxide, and you don't have a curtain anymore. But probably you forgot already what it means to take an airplane. So the tungsten oxide has a very nice property that upon reduction, okay, you change the redox state of the tungsten from tungsten 6 to tungsten 5 more or less, and by that you change the color from almost colorless to very strong blue, and this is indeed called tungsten bronze. And again, because what you can do here is you can simply reduce partially the negative charge of the nanoparticle, and then you can drive the deposition. And this is shown here very nicely. So this is the actual nanoparticles, this is the film which is formed, and we show very nicely, and again, very shortly because of the time, that what we get is we get a film which is made of nanoparticles of tungsten oxide, and they actually behave very well. They have a very strong contrast, and the coloring and the bleaching time is very short as compared to continuous film of tungsten oxide. And the reason for that is their nanoparticular structure and nature that enables the ingress and egress of lithium ions going inside. And just very briefly also, because most of the community, the electrochemistry community in Israel now is dealing with energy storage, as you can hear here. So we can, and this is only the very beginning, you can think about making materials for batteries and supercapacitors by the same way. And the advantage here is that you make the electrodes with a binder free, and because of that, basically, we should be able to increase the capacity and the performance of such electrodes. Very, very briefly, because I think that also my time is running out. So one way of doing that is the electrode deposition of graphene oxide. Doron again spoke about the graphene oxide. Graphene oxide can be deposited electrochemically, and we were not the first one to do that, by electrophoretic deposition. In electrophoretic deposition, which is carried out at very high potentials, the graphene oxide is negatively charged, which means that you have to apply positive charge and the graphene oxide will be deposited. But to do it the other way, electrochemically, at very relatively mild conditions, is to apply negative potential, which partially, again, reduces the carboxylic acid and other oxygen functionalities on the surface, and because of that, in this case, it will be deposited on the negative electrode. And we did one example. I'll go very quickly by that. So we are working on lithium-ion capacitors, and basically we are working on supercapacitors. And again, the challenge is to increase the specific energy of the capacitor. And by that, what we were doing is we were depositing the graphene oxide by reducing it, and then added type of vanadium oxide inside as a battery type material, and by that we can increase very much we can increase the specific energy. A big advantage of this electrochemical deposition in this case is that we want to actually generate also hydrogen in order to make the reduced graphene oxide very porous and with very high surface area. I will skip all these are characterization, but again, because of time, let me skip that and just jump to the end. Say that what I wanted to show you and the message I wanted to convey was, first of all, there is still a lot to do with electrochemical deposition. I think that, again, as I said before, the ground is open for many more players. One is the indirect electrochemical deposition, the fact that you can deposit almost any type of material if you understand how to destabilize it, or how, for example, you can electropolymerize it, like in the case of the soldier. The other thing is the position of nanomaterials. This is only the very beginning. There are not so many papers and not so many works about the electrochemical deposition. Again, it's not electrophoretic deposition. Electrophoretic deposition is carried out in non-aqueous solution, mostly at very high potentials. We are talking here very mild potentials that you don't affect any drag that you have there and so on. And you can do almost anything you want if you understand what are the forces that you have between the nanoparticles and how, by electrochemistry, you can control these forces. And let me only acknowledge the people who did the work. Most of this work actually was carried out by Liang Liu, who is currently now in France. The other people like Chang Liu and Yi Chang are from Singapore. Ori Geuli also did a very nice PhD in my lab and now works in a high-tech company in Israel. And again, I'd like very much to thank you for your attention.